Thanks, Dunne. Let me begin by thanking the organizers for organizing this interesting school. It's also very nice to be back in Seoul again. It's been a long week. I don't know about you, but I'm a little tired. So it's Sunday afternoon. Today's lecture will be relatively straightforward. So I'm going to give an overview of resurgence. It's a relatively technical topic, but I'm going to keep things simple for these lectures. If you're curious and interested, there was a research program at KATP a year ago, and there are many talks online that you can look at, and quite a few of them were tutorial level talks about various applications of resurgence as well as a mathematical background. So if you are interested, I invite you to go Google KATP from 2017 and have a look. I also announced that there'll be a 6-month program in a couple of years at Newton Institute. Okay, so here's a rough plan. I would only take seriously the first two because we'll see how far we get. Today I'm just going to introduce the basic ideas. It'll be fairly mathematical, but very simple mathematics. And I'll show you some examples to give a feel for how things work. Tomorrow I'll talk about applications in quantum field theory and quantum mechanics. And then, depending how much time we have, I want to talk about large N, and I'll do it in the context of some quantum mechanical models along the lines of the ODE integral models that Shota mentioned, but I'll do it in the context of all orders WKB. And if we have time, I want to talk about some more recent work about the relation to phase transitions. And I'd like to work through a famous example, which is the Gross-Poitier unitary matrix model. So my perspective is not to try to give you any proofs of anything. I'll give you some statements, some motivation, and then just do some examples, okay? That's the strategy. And there'll be some exercises sprinkled through the notes. And today I'm going to use the projector because I have to show you lots of figures and pictures. And I think adiabatically I'll move to the board as we for the next lectures. Okay, so let's begin with some motivation. The motivation is some really big problems. So I'm not going to be able to give you the solution. These are really outstanding problems, but it's worth having big goals. So we want to find a non-perturbative definition of quantum field theory complementary to the one from the lattice, because there are some problems in physics that the lattice is not able to address. One of the things you confront immediately when you try to think about things like this is, what does it mean to analytically continue a path integral? And we've heard through the lectures this past week questions about non-equilibrium physics, but also there's a related problem with the sign problem that are related to the idea of trying to analytically continue path integrals. Along the way, we're going to discover some new magic in perturbation theory that's unfamiliar and surprising. And we'll be able to use this to get some new understanding of weak-strong coupling dualities. And I'll talk about some of these applications as I go along. Okay, so here's a big goal, phase diagram of QCD. We can do things out here, we can do things out here, we can do things near here. The interesting questions are in the middle. How do we access things in the middle from asymptotic information far away? Okay. It's a very, very general question. There's no general answer because it's a big question, but resurgence gives you new tools for actually doing these sorts of extensions. So the sign problem that I mentioned is that if you try to write down the lattice representation of QCD at finite density, then this fermion determinant is complex because of the chemical potential, and so conventional Monte Carlo techniques fail. So that's generically known as the sign problem. It's not just a problem in QCD. It's very well known in atomic physics and condensed matter physics and physical chemistry. Anything new you learn about this problem is valuable. And I'll also talk as we go further along about phase transitions using Li-Yang zero language. The Euclidean path integral is designed to be good for equilibrium thermodynamics. It reduces essentially to statistical mechanics. But there are problems that are non-equilibrium. They don't correspond to the Euclidean path integral. You have to deal with these Schwinger-Keldysh contours that we also heard about last week. And they necessarily require understanding what it means to have complex contours in a path integral representation if you want to go beyond perturbation theory in some strong coupling problem. So that's more motivation. So think, in the back of your mind, think of this question: how does this genuine Minkowski path integral relate to the Euclidean path integral? This is clearly a big problem for quantum gravity also. And this goes back to the work of Stokes in the 1800s, where he was considering the Airy function. He was working on supernumerary rainbows, repeated rainbows. And he only had techniques for studying the behavior near the origin, but he was interested in explaining these oscillations on the dark side, on the bright side of the rainbow. And we're all familiar with the fact that here's an integral representation of the Airy function. X is the variable, the argument of the Airy function, but it's written as an integral over t. And clearly when x is large, the integrand is a horrendously oscillatory function. And there's simply no way you can do that integral. Okay? You cannot do that integral numerically. You cannot do it by Monte Carlo. It's simply impossible, okay, as a real integral. Right? If you think of x equals 5, all these cancellations between positive and negative have to happen to give you an answer that's 10 to the minus 4. Okay? So, the answer, of course, is very well known. You can bring this problem under control by deforming the contours, and we'll go through this example in great detail today. And you learn that when x is positive, one saddle point contributes, and you have this exponential decay when x is positive. Whereas when x is negative, there are two saddle points that contribute, and you get this oscillatory behavior with this interesting phase shift pi over 4, which was actually Stokes' big contribution to this problem. So if you look at this and this, what we're trying to think about is some sort of functional version of controlling this type of path integral expression by doing some analytic continuation, deformation of contours, whatever that means. That's what we're going to talk about. So the mere fact that in one-dimensional integrals we need complex analysis in order to bring an oscillatory exponential integral under control, it doesn't tell you you have to do that for path integrals, but at least strongly suggests that you should consider the possibility of making sense of what it means to analytically continue an infinite dimensional integral into the complex plane in terms of steepest descent contours. Okay? So this is clearly an obvious idea. People haven't taken it fairly seriously until quite recently, and just in the last couple of years there have been some genuine implementations by lattice people of this idea, and so far it's working quite nicely, even though there are serious technical problems to overcome in any given model. So that's some physics motivation. Now for some mathematics motivation. So this funny word, resurgence, which I'll tell you what it means in a few slides, it's a moderately new idea in mathematics. The name was coined by a French mathematician, Jean Icard, in work in 1980. But the ideas go back to this work of Stokes from the 1850s. I'll give you various definitions as we go along of what resurgence is, and they'll be slightly different depending on the perspective. But at the beginning, think of it as a unification of perturbation theory and non-perturbative physics. Okay, so now I gave you a definition, but I have to tell you what it means by unification. But you should know already that perturbation theory generally gives you divergent series. That's the normal behavior. It's not the only behavior, but it's the generic phenomenon. And the first step on the road towards resurgence is to generalize the concept of a series, a formal divergent series, to something called a transseries. And I'll define that as we go along and give you examples. But roughly speaking, a transseries is an extension of a normal Taylor series that also includes non-perturbative terms like exponentials and logs, okay? But includes them in a clever way. And the goal is that the transseries is actually well-defined under analytic continuation. So I also have to tell you what that means. But as soon as that becomes true, if you have an expansion in terms of both perturbative physics and non-perturbative contributions, such that they're well-defined under analytic continuation, that automatically tells you that the perturbative expansions and the non-perturbative expansions have to be related to one another. Otherwise, it can't work. Okay? So this is the goal. So it was developed to great advantage in differential equations, both ordinary and partial. Difference equations, it's been applied a lot in fluid mechanics, mundane problems like aircraft engine flow, believe it or not. Really complicated nonlinear problems like that. In physics, our type of physics, fluid mechanics is physics. Tell that to Stokes. It's been applied more recently in quantum mechanics, matrix models, field theory, string theory. And we're still in early stages of exploring and testing it on this model and that model, but slowly building up some experience. And it seems to be working very well, often better than it should. And so one other aspect of resurgence is that the way we usually think of saddle point approximations are as approximations. But the idea of resurgence is that you can go beyond that and actually use it as an exact definition of an integral. So we also have to see what that means. So just some things to make sure we're all starting off from the same place. There are very few soluble problems in the world, and there are even fewer interesting soluble problems in the world. Most difficult problems, one of the only ways we can address problems analytically is by making expansions in some parameter. Okay? That's clear. Often, but not always, these turn out to be divergent expansions. I'll actually talk in the later lectures about resurgence in convergent expansions, but most of what I talk about today and tomorrow will be about divergent expansions. But often this is the best we can do, and sometimes it's the only thing we can do. So it's actually useful to try and understand how much information we can extract from some perturbative expansion. And one of the messages from resurgence is that there are new techniques for extracting information from formal series. New in the sense we weren't taught it from our textbooks, and it's not yet really in the standard textbooks. And along the way, we'll learn some interesting physics about non-perturbative physics from the point of view of perturbation theory, but also vice versa. How to use non-perturbative physics to tell us something about complicated perturbative problems. So, I don't know if you saw some sad news. Michael Atia died yesterday. And he's had a huge influence on our field, so I think it's appropriate to acknowledge his huge impact on what we do and what we've done. And in the obituary I read this morning, there's this very nice quote talking about the index theorem that is kind of amazing that you can learn something without solving an equation. So it's kind of in the spirit of resurgence, is that you can learn something about a very complicated theory without actually solving the theory. Okay? So you probe it using special techniques, but you don't actually find the exact solution to the Schwinger-Dyson equations or whatever. But it doesn't mean you can't learn something precise about the theory. So let's begin. I'll tell you first what a transseries is, then I'll tell you what resurgence is, and then we'll do a bunch of examples. Okay? So there's this famous book by Hardy about divergent series. And he makes this interesting comment that no problem he had ever seen couldn't be solved in terms of powers of a variable, exponentials in the inverse of the variable, and logarithms. It's sort of a throwaway comment that he made that anything he'd ever seen in his life could be analyzed that way. So fast forward to 1980, Jean Carl was solving problems in dynamical systems. He was actually addressing one of the Hilbert problems to try and identify qualitatively how many limit cycles there are in complicated dynamical systems. Okay, well, I think it's enough to be able to read this one. Right? If this one goes out, we're in trouble. So Carl was studying these sorts of systems where you need to be able to control Lyapunov exponents, these incredibly small deviations, the sensitivity to initial conditions and conditions near separatrices. And that's what led him to develop the concept of a transseries and resurgence. Carl essentially proved this observation by Hardy, is that any asymptotic problem you want to do can be expanded in terms of these three basic quantities. Interestingly, in a completely different field of mathematical logic, at almost exactly the same time, it was discovered that these transseries, these objects made out of x, log x, and e to the minus 1 over x, formed a closed logic system. It's kind of surreal that this was discovered at the same time by completely different people. So let's be a bit more precise now. Carl defined a set of resurgent functions, which are, it's a bigger class than analytic functions. They're called analyzable functions. And these functions are closed under all mathematical operations. So that sounds suspicious, right? But if you think of a Taylor series, the Taylor series is not closed under all operations, because if you invert a Taylor series, you're out of the system. So now you might think, okay, I'll deal with Lorentz series. Okay, fine. Well, now integrate. Well, now you just created a logarithm. Now invert it, 1 over logarithm. If you integrate it, now you have a divergent series. Right? So you immediately spiral out of control, you would think. And Carl was addressing the question, is there some closed set of functions under all mathematical operations? And to us, all will mean things like Borel transforms, analytic continuation, Laplace transforms, as well as the obvious ones of convolution and integration, etc. And the surprising thing is that there is an answer to this. And that's what's called a transseries. Now in physics, the way this shows up is that you generalize a series in powers of a small parameter g squared to also include things like this, which cannot be expanded in powers of g squared, and also powers of logarithms, which themselves cannot be expanded in powers of g squared. And this is a common form. It's not the only form, but it's a common form of the way a transseries appears in physics. Technically, to the mathematicians, you should iterate exponentials and logarithms, and that's a full-blown transseries. But of course, in physics, we also are familiar with examples where you have logs of logs of logs from certain Feynman diagram, classes of Feynman diagrams. So at this point, you say, well, this isn't that interesting because we know this already. This is just multi-instanton calculus. But the fact that you put them together into one object with some coefficients, and so you're summing over a perturbative direction, a non-perturbative direction, and something that I'll call a quasi-zero mode direction. The fact that you unify this into one object called a transseries has some interesting consequences. So the interesting consequence number one is that this object can be appropriately defined, well-defined under analytic continuation. Now remember, that's not true if you just have a formal series. And I'll show you some examples of this as we go along. If you have an asymptotic series, it's well-defined along a particular line. It's not well-defined when you start analytically continuing it off that line. A transseries is. The fact that that's true tells you immediately that these coefficients in the different directions have to be correlated. And then the question is, are they correlated in an interesting way or a boring way? And it turns out to be very interesting. And if you're interested in numerics, you can get essentially exponential precision in non-perturbative calculations. Again, I'm going to show you lots of examples as we go along. So, yes, I'll get to that. These logs in these applications I'll talk about come from interaction between instantons. So K is the instanton number, so it's pairwise interactions between instantons. So where does this funny name resurgence come from? So here's a quote from École, translated from French into English. So resurgent functions display at their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up at their singularities. So I've tried to draw a picture to translate that into pictorial language. So just imagine you have some problem, and it really doesn't matter what your problem is. It could be a set of differential equations, integral equations, difference equations, could be an integral, it could be multidimensional integral, an infinite dimensional integral, it doesn't matter. And imagine there's some parameter that you want to expand it. And imagine there are some special regions of that parameter. It could be a critical point, it could be infinity, it could be zero, it could be some singular point, it could be a saddle point. And imagine you have some way of doing expansions around those special points. Okay? And imagine there's more than one of them. So the general statement is that there is essentially always connections between the fluctuations around the different special points. Okay? So that's the idea of resurgence. In principle, if you knew the behavior of the function in the neighborhood of this point, you could resurge the properties of the function at other critical points. Okay? Now, I don't know about you. When I first heard this, I said, no way. That's impossible. That's ridiculous. Because you're doing some sort of local analysis in some region, and there's a claim that you can somehow extract some global information from that local analysis. So this violates the no free lunch theorem, and you should be very suspicious. Okay? But I will hopefully, by the end of the lectures, convince you that there are a number of cases, very explicit cases in physics where this really happens. So in this line, a mathematician might define resurgence this way. We all know that complex analysis is very powerful, very useful, and beautiful subject, extremely elegant, but it's built on analytic functions, okay, with twists about meromorphic and branch cuts and whatever, but it's built on the foundations of analytic functions. So suppose you wanted to construct complex analysis that could deal with not just analytic functions, but also formal divergent series. So in a way that, hold on a second, hold on. In a way that you can still do manipulations like monodromy, analytic continuation, Borel summation. So that's the one way of stating the goal of resurgence in terms of function theory. Yes, question?
So the number of the critical point is finite or?
Can be infinite.
Can be infinity.
I'll show you an example where it's infinite.
Okay.
You should remain suspicious.
Okay, thank you.
We're physicists. We should be suspicious. Okay, so just some words about perturbation theory. Now, I warned you, today's lecture is going to be very simple. I want to really start with very basic things today and work our way up. So perturbation theory is very useful, but of course it has drawbacks, because essentially any problem that you studied as an undergrad, or even in grad school in quantum mechanics, perturbation theory is divergent. So the Zeeman effect, the Stark effect, factorially divergent. The cubic oscillator, quartic oscillator, factorially divergent. The periodic potential, the symmetric double well. These are the two famous problems that you learn when you're starting to learn about instantons. Perturbation theory in these cases are also factorially divergent. So there's a pattern here. And I want to convince you that this is actually not a bad thing. This is actually an extremely good thing that they're divergent, because divergent series have a lot more information in them. And they're actually a lot more precise numerically, provided you treat them properly. Okay? They're much more useful than convergent expansions in many contexts. Also, keep in mind, perturbation theory works, okay? When treated correctly, in the right regimes, QED, of course, is a famous classic case. 13,000 Feynman diagrams, 5 loops, it really works. Even in QCD, in the appropriate regime, perturbation theory really works. So let's just keep that in the back of our mind to keep some perspective here. So let's remind ourselves what a divergent series is. So imagine some series, you're expanding it around some point x0, there are some coefficients, this is the partial sum, and there's some remainder. Okay, and in principle, you would like to sum to infinity, but in practice, of course, you can never sum to infinity. So a convergent series is that this remainder goes to 0 as n goes to infinity with fixed x, provided you're in the radius of convergence. It just means you do more work and you get a better answer. Okay? Add more terms, it always gets closer. An asymptotic series is very different. An asymptotic series is this remainder goes to 0 with n fixed, but x going to the point you're expanding around. Okay, so it's a very, very different type of limit, and it leads to the concept that is in all the math physics textbooks of optimal truncation. So I'm going to show you this by some examples. So let's look at the most famous examples, the example that Euler treated first. It's the expansion of something called the exponential integral function, and it has an expansion alternating in sign, and the coefficients are just n factorial. So you will all agree this is definitely a divergent series. And here I'm just plotting at a particular value of x, and as a function of this truncation of the partial sum, here are the values. And the red line is the value of this function at that point, x equals 0.1. So it's an alternating sum, so it goes like this. It oscillates around the actual value. Then after a certain point, it starts diverging again. If I change x to 0.2, here in this case I'm expanding around x0 equals 0. Right? So if x is now a little bit bigger, the same pattern that it's sort of trying to converge to the value and then starts diverging. So this type of behavior is completely generic for asymptotic series. Okay? The precise details might be a little bit different, but this general behavior of tending towards a particular value and then beyond a certain order in the truncation, diverging again, is generic. And you'll notice that the order at which you should truncate to get closest to the actual value goes like 1 over x. So here when x is 0.1, it's roughly about 10. When x was 0.2, it's roughly around 5. Okay? So homework exercise number 1, prove that. So the idea is you look at the values of the summands for a given value of x. So you fix x, and you minimize this with respect to n. And you'll see that the minimum is at n of the order 1 over x. And then repeat it for 2n factorial instead. See what happens. These slides will be online. So, now what about the non-alternating version of this, n factorial? Not minus 1 to the n factorial. Well, now it's not going to be oscillating, but the same thing. It goes towards this value around about 10, and then it starts going away. Likewise here. Actually, the optimal truncation value is this value minus 1. But since we're going to be able to do infinitely better than optimal truncation, I don't really care. Okay? But this is in a lot of the physics books, this idea. Contrast that with a convergent series, like this polylog guy. You just add more terms and it gets closer and closer. Right? Independent of x. Well, within the radius of convergence. So I've discovered in talking to people over the last few years that people have this, physicists have this somehow synaptic connection in their brains that divergent means bad. So I'm going to try and break that synapse. Okay? This is sort of the secret goal of my lectures. So here's the first attempt. So here's the Airy function. And I don't know if you can see it, the sort of opaque blue curve is the exact curve on the negative axis. The red one is one term of the asymptotic expansion around x equals minus infinity. One term. The green line is 10 terms of the convergent expansion around 0. Now remember, the radius of convergence around 0 is infinity. This is as convergent as you're going to get. And if you take 50 terms, you get this, the black line. Right? So I don't know about you, but one term is a lot better than 100 terms, 50 terms. And this asymptotic expansion is remarkably accurate. Okay? And we'll see that again and again through these lectures, that you can get great precision from, let's call them semi-classical approximation, non-perturbative physics, often much, much better than a much, much higher order perturbative calculation. Now, the way I described an asymptotic series, there was this remainder term that was bounded by it was essentially the next term in the series. And so the remainder term here would be n factorial x to the n at the optimal truncation point. So it looks like this is power law correction, right? It's x to the n. But because x and n are correlated at the optimal truncation point, remember, this is the big difference about an asymptotic series. The point at which you should truncate depends on x. You change x, you should have either more or less, fewer terms in the expansion. So when you run this through the Stirling formula, you see that actually the remainder term is exponentially small. Okay? For small x. So here I've drawn these bands of this exponential correction for x equals 0.1 or 0.2. And so the way it's usually presented in mathematical physics books is there's this sort of fuzzy region of unknowability, which is exponentially small. And this is actually simply completely wrong. Okay? So part of the goal of Resurgence is to probe within this region. And we can actually learn a lot, even just from the series itself, about this region. So it's unfortunate, but a lot of the textbooks are simply missing the point. So to proceed, we need some way of controlling divergent series in a way that we can actually do something with them. There are many, many ways to do it. People have had a long time to think about this. One of the best, most adaptable, and most practical, both from the mathematical point of view and the physics point of view, is called Borel summation. There's also vast literature on this, but I just want to tell you basically how it works. So imagine you're confronted with this famous n factorial problem. So we learned in high school that n factorial can be written as this integral. You just successively integrate by parts. You get an n minus 1, n minus 2. So imagine you replace this n factorial by this integral. And we're physicists, so we happily interchange the summation and integration. If you do that, you can now do the sum very easily. And it's a geometric series. So you get this integral. Okay? So that integral is completely finite and well-defined for any positive x. So the basic idea is to take that integral as the definition of that series. Or in other words, you should actually read this formula in Hebrew. You should read it backwards, from right to left. That this is the answer. And if somebody asked you, what's the small x asymptotic expansion of that answer, which is completely well-defined, you would write down this, okay, rather than the other way around. Now, unfortunately, in the real world, we're often stuck with doing this first. So the whole literature about Borel summation is under which circumstances is it okay to interchange? Right? We all laughed, right? But there are theorems about under what circumstances it's okay to do that. So that's very interesting, but unfortunately, in really difficult problems in physics, often those theorems are not particularly useful because very often we don't know enough to satisfy the fine print of these theorems. We don't know enough about the analytic structure of a mass gap or something. We have some intuition, but we don't actually know. So often the way we are just simply forced to proceed is experimentally.
I have a question.
Yeah.
And
I can't see. Okay.
if some genius find another integral representation of the m factorial, yeah, if someone finds some another integral representation of the m factorial,
Yeah.
and do the similar find some other formula, will it give the same like
Of course,
physics
it's
later?
just a change of variables or a change of contours. If it's the same.
Is it same like some other integral, like there would be many m factorial
Of course.
integral representation.
But they're just related by changes of variables or
Always.
deformation of contours. So
Okay.
anyway, let's not worry about it. It's not important. So here's a picture. Here's this function as a function of x, the red line. If you plot successive orders of the expansion, the first one is just this straight line. You just have x. And then you start getting curves. And you notice that as you take more and more terms, it gets worse and worse at large x. Right? Because at large x, the optimal order goes like 1 over x, so the optimal order is smaller. Right? Again, completely generic behavior of asymptotic expansions. Now, more physically interesting is what happens when you get rid of the minus 1 to the n. So, at least at a formal level, it's just changing x to minus x, right? So if you follow the same procedure, it looks like you get 1 minus xt here. This gets 2 question marks because now we have a pole on the t-axis if x is positive. So now we have to decide what do we do about that pole. And this is actually a very interesting problem because you see, at very least, what's going to happen at that pole is you're going to pick up a contribution which goes like e to the minus 1 over x. And it'll have some imaginary multiplier. And it might be plus, it might be minus, it might have the factor of a half, who knows, depending what you do with that pole. Okay? Now this is very strange because I gave you a series in which every term was real, and yet I'm telling you that with Borel summation, you will find a non-perturbative term, moreover, an imaginary non-perturbative term, moreover, an imaginary non-perturbative term where it's not obvious what the sign is.
Sorry.
So
Excuse
wait a
me.
second.
Oh, okay.
We really need to understand this problem. And I'll show you some examples where physics resolves this problem. Okay? And actually, proper Borel summation resolves this problem. I showed you just a very sloppy version of Borel summation to start off. Yes?
Excuse me, a naive question. Does this xt is smaller than 1? If it's not, why can we do this summation?
Sorry?
Does xt is smaller than 1?
Okay. So I'm not giving you the truth with Borel summation here, right? This is supposed to be an expansion at small x. These are formal expansions. The question is, when can you do this? I don't want to get into those details, okay? This is not a course about Borel summation. All right, now this example is very interesting because remember, this is this function. So we actually know about this function. We know about its real and imaginary parts. And I can take x to be negative, and I can plot the real part, and the real part looks like this red curve here. If you look at this sum, there's no way you're going to convince this sum to turn over. Okay? And yet, that's what it needs to do. Whereas the principal part of this integral does exactly that. It's this dotted line underneath here. Okay? So even though this looks very suspicious, there's some truth here somewhere. And this is what we want to try and understand. Moreover, this function, this exponential integral function, as a function in the complex plane, has a connection formula, which is that as you rotate the variable, there's an analytic piece, there's a logarithm, and there's a plus or minus I pi, depending which way you rotate, which gives you this exponential, which turns out to be exactly this exponential. Okay, so even though this looked extremely suspicious, it's actually exactly correct. So the message here is that this Borel method is capable of starting with a series, a formal series which is divergent, and it's capable of explaining non-perturbative connection formulas. Okay? I've just shown you one example, but that's a general statement. Yeah.
For a realistic theory, like QED or QCD. What is the typical order after which I will see that my results gets bad?
I'll talk about that later. I'll talk about field theory tomorrow. Okay, so here's a more formal definition, slightly more formal. Imagine you have a formal divergent series. These C's are growing factorial in some way. You construct a new function which is called the Borel transform of this function, which is the same series but in a different variable, the Borel variable. And the coefficients, you just divide every coefficient by n factorial. Okay, so that's a very simple prescription. Now, if you divide by enough of a factorial, this will now be a convergent series. Okay? So this function, this Borel function, has a finite radius of convergence. And the idea is that you get back to the original function by integrating this. And if you just do it term by term, you see that each t here, when I do this integral, gives me an n factorial, which cancels that one, and gives me powers of g. Right? So all we've done is we moved the problem of trying to understand this guy to understanding this guy. Okay? We just shifted the problem from one place to another. But there's a big advantage here, because we moved this into a realm where we know what to do. And so the idea of trying to understand the structure of this function, or this formal series that's trying to be a function, is to try and understand the analytic structure of this function, the Borel transform function. And generically, it will have singularities such as poles or cuts or whatever, and those contain interesting physics. So for example, imagine there's a pole. I could rotate this contour above or below, and the difference between these two definitions along these two different contours is just the contribution at the pole, if that's the only singularity. So there's this non-perturbative difference between the integral defined along this contour and along this contour. If you're able to keep track of how this function changes as you rotate contours, you're carrying with you all this non-perturbative information. And that's the idea of a transseries. All right. So how does it actually work in practice, in real problems? For reasons that are not totally obvious, in almost all problems you'll see in physics, the coefficients tend to grow factorially. And there are three interesting parameters. There's a power out front. It could be n factorial, it could be 2n factorial. In principle, it could be 3n factorial or something. And it could be n plus a half, or something like that, right? And if you repeat the argument, so this is exercise 2, repeat the argument of writing the integral representation of this and then doing the integral, you'll discover that the representation of this function is now this integral. And you see that if there's a beta to the n, it's clear that you should just include beta with g. Right? There's no reason not to write beta g as the new expansion parameter. So everywhere here, you have beta g. What's less obvious is that if there's gamma here, you get a 1 over gamma. And if there's a delta here, it affects a prefactor. And if you do this for the imaginary case, the structure of the non-perturbative contribution depends on these parameters. And we'll see an extremely non-trivial example of this, probably not later today, but tomorrow. So knowing this parameter here, knowing whether it's n factorial or 2n factorial, immediately tells you in any non-perturbative contribution you see, is it g, 1 over g, or is it 1 over root g? Or is it 1 over g to the 1/3? Right? Just from knowing that number. So that's amazing. If you know beta, you know that it's not really g, it's really beta g that you should be expanding in. That's interesting. If you know this delta, you learn the leading prefactor. Okay? So this is the first sort of glimpse of something about connecting perturbation theory to non-perturbative physics, knowing something about the large order growth of perturbative coefficients immediately tells you you should expect, it doesn't prove anything yet, but it tells you you should go look for some non-perturbative object behaving like that. Okay? And we can quantify that, make that much more precise as we go along. But that's a sort of teaser to get you interested. So exercise 2, check those formulas. It's not difficult. Okay, so another way to think about resurgence is that if you make an asymptotic expansion, it doesn't satisfy analytic continuation properties, but resurgence can fix that. So let me show you an example of this. But you should still be suspicious. Is this actually true? And if so, even if it's true, is it actually useful? So let me give you an example. You've seen this example in many problems in physics. It's the Stirling expansion. Now, instead of talking about the gamma function, which is products of things, I'm going to talk about the log of the gamma function, which is sums of things. So I want to talk about sums. And I'll talk about this digamma function, which is the derivative of the log of the gamma function. Okay? So at large Z, these first two terms are what you get from the leading Stirling approximation to gamma of Z. Okay? I'm sure you've all done that calculation. Well, here's the rest of the series at large Z. So you do 3 more terms and you think, oh, great, this is a wonderfully convergent expansion. We're in business. If you go a little further, you start realizing, well, no, sorry. The coefficients grow like 2n factorial. They're actually Bernoulli numbers. Okay, so this is a divergent series around Z equals plus infinity. And it's consistent with this functional relation. So what do we know about the gamma function? We know that Z, gamma of Z, is gamma of Z plus 1. Right? Which is an infinite order differential equation, right? Gamma of Z plus 1 is e to the d by dz on gamma of Z. Right? It's just a shift operator. Right? So this expansion is consistent with that functional relation. So that's good. But we know one other fact about the gamma function. What else do we know? Right, to derive this, all you need is that integral representation, which is valid for Z positive. But we know the reflection formula to Z negative. Right? We know that gamma of Z, gamma of 1 minus Z, is pi over sine pi Z. Right? This is the reflection formula. Right? It's a global property of the gamma function. It's what allows you to analytically continue everywhere in the complex plane with just isolated poles at the negative integers, 0. Right? Now, that's a property of gamma of Z, but I can translate it into a property of psi of Z, obviously. And this is what it looks like for psi of Z. Okay, well, it turns out this expansion is not consistent with that property. It's easy to see. Imagine you take this and you try to rotate it to the imaginary axis. So let's look at this expansion. All the red stuff is an expansion in Z squared. So when I go Z, write Z as IY, I don't get any contribution from those terms, right? So the imaginary part of this when Z is imaginary, Z is IY, just comes from these two terms, so it's these two black terms. Okay? However, from the reflection formula, when Z is I times something, you get an infinite series of exponentials. Okay? So there are 2 ways to view this result. One is you could look at this expansion and say, I want this to satisfy the reflection formula. Okay? This is like from Shota's talk, you compute an S matrix and you want it to be unitary. Okay? You impose some physical condition on it. And you notice that your expansion does not satisfy that condition. But you're clever, you can work out what you need to add to it, which is exponentially smaller than the things you were dealing with, in order to make it consistent with the expansion. with the condition. And you discover that those terms and only those terms satisfy that condition. Okay? So this idea that you cannot know anything about these exponentially small terms, clearly false in this case. The other way to look at it is you could take this series, you could Borel sum it. Now you have an integral representation which you can analytically continue properly. And you discover that when you analytically continue to the imaginary axis, there are some poles. The residues of those poles give you exactly these terms. Okay? So it just means that if you're too naive in manipulating an asymptotic series, you get nonsense. But there are ways to do it properly. And the ways to get it properly specify exactly what the exponentially small terms must be. So this is an example of what we would call a non-perturbative completion, that from some perturbative information plus some global symmetry property that we know must be true, we can combine those two to complete the perturbative expansion in a precise way. Now this may look a bit simplistic, but this problem shows up all over the place in our type of physics. So I've already said this. Here's the Borel representation, has some poles on the imaginary axis. These give you exactly those exponentials. And this example shows up all over the place in quantum field theory. The Euler-Heisenberg effect of action, finite temperature, these are just Matsubara modes, de Sitter space, exact S matrices, et cetera, et cetera. They all boil down to exactly that problem on the previous slide. So here's a list. Here's the Euler-Heisenberg effect of action. Here's the Gaussian matrix model. Here's the C equals 1 string, free energy, Chern-Simons matrix model. It's just the same problem. Okay? Same Borel transform argument. So it's not a superficial statement to say that we have a possibility of reconstructing non-perturbative completions by doing this sort of Borel manipulation precisely. Okay, but even that case in the world of really complicated field theories, things like Yang-Mills, things where you have asymptotic freedom and genuinely running couplings, this is too simplistic to just have pure poles in the Borel transform which just give you exponentials. What we typically expect is we expect exponentials corresponding to instantons, but we expect there to be fluctuations around the exponentials. We expect those fluctuations to themselves be asymptotic series. And the way that's captured by a Borel transform is not by poles, but by cuts. So for example, here's the incomplete gamma function. It's a function of two variables, S and X. And here's its asymptotic expansion. Here's its Borel representation over here. The Borel function has a branch cut at -1. And the order of the branch cut depends on this parameter S. Okay? So here's the expansion. There's an exponential from the branch point, and then it's multiplied by a series, which is an expansion around that point. And that's a factorially divergent series. I could have put this gamma up here using the reflection formula. But notice there's something very interesting about this expression. If S happens to be an integer, then it's actually not a branch cut. It's just a higher order pole of some sort, or even a zero. In which case, this truncates. And this is a phenomenon that happens in physics. For example, supersymmetry, for example, localization. You can be considering a problem that has some parameters in it. And those parameters might be numbers. They might be numbers of flavors, numbers of colors. They might be the dimension of your manifold. When those numbers take integer values, interesting things can happen. You can get interference effects between different saddles, and asymptotic expansions can truncate. This is actually exactly what localization is. In principle, you should have an infinite sum over saddles, but under some circumstances, when there's enough symmetry in the problem, it can truncate to the contribution of a finite number of saddles. Okay? And what should be formally divergent series can truncate to become convergent. They can truncate to be just one term. It can truncate to become zero. So this phenomenon is something that's quite generic, and it's important. I'll be talking a lot about this in the third and fourth lectures with examples. That resurgence becomes much more interesting and much richer when you have more than one variable. It's called parametric resurgence. And this is exactly what we want in physics, because we don't want to be just stuck with describing expansions in a fixed small parameter. In quantum field theory, we want to be able to expand in fixed parameter, but maybe a number of flavors, number of colors. We want the parameter, the coupling, to be able to run. So we want to be able to take care of all this extra level of structure. Okay. So I want to talk now about differential equations. So if you have I'll talk first about linear differential equations, and then tomorrow we'll talk about nonlinear differential equations, where interesting new things happen. So if you have a second order differential equation, you know from WKB that there are basically two types of exponentials, right? There's e to the plus, e to the minus. If you have an nth order differential equation, there are n different types of exponentials. So the solution to a differential equation, linear differential equation of nth order, you construct this Borel transform, it will have generically n singularities. So once you have more than two, interesting questions start arising about how they're related to one another. Are all the saddles really related to each other, or are some of them only related to some of the others? This is called Picard-Lefschetz theory. So let me tell you something which I hope is surprising. Something about ordinary contour integrals. So imagine you're trying to do this particular contour integral here. There's some action function z, and imagine it has a certain number of critical points. Let's take it to be finite for now, but it doesn't really matter. Just more than one, more than two. And there's some small parameter g. So imagine that f has some number of saddle points, critical points. So once you tell me which critical point to look at, and I can construct the steepest descent contour C through that saddle point. Okay? You know how to do that. So that integral is now completely well defined. It's the steepest descent contour. So I can take the leading contribution, which is the value of the function at the saddle point. I can do the Gaussian fluctuation near the saddle point, which gives me the prefactor. That's usually where we stop. Okay? So what I want to convince you of now is that there's a huge amount of physics thrown away in that step. If you look at the rest of the expansion. Okay? So this is work from Michael Berry and Chris Howells, studying something called hyperasymptotics. So imagine this is the remainder series. It's a series in G squared for this well-defined integral along that steepest descent contour. So there's nothing complicated about that integral. You can generate as many terms as you want in that expansion. So something incredible happens when you look at the behavior of this series. So I'm running out of time, so let me not go into the derivation, but you can prove that the series around saddle point labeled by n is exactly equal to a sum over all the other saddle points with some directional factors depending which way the contours go, of some integral transform of the fluctuation series around saddle point m. And it's nothing more than deforming contours. You just deform contours around, wrap them around, keep track of everything. But this formula is interesting because g squared only appears here. It doesn't appear here. Sorry, fnm is the difference between the function at n and the function at m, capital FNM. So g squared appears here, so I can expand in g squared. So that tells me immediately a relation between the fluctuation coefficients around here and around here. And what it looks like is that, first of all, the fluctuation coefficients around this point at large order grow factorially. We already saw lots of examples of that, right? Well, this is why. It's completely generic for any integral. And it's a sum over contributions from, in principle, all the other saddles. I'll qualify that statement shortly. And the leading coefficient is the 0th order coefficient around the other saddle. And the power is the difference of the function between the two saddles. That's the leading behavior. There's a subleading behavior, which is r minus 2 factorial. Remember, this is the large order behavior around saddle n. The subleading one has one more power of the function difference, and its coefficient is the next coefficient around saddle point n, and so on. Okay? Now, let me let that sink in for a second. This is amazing. Any contour integral you care to do with a number of different saddle points has this hidden structure in the saddle point expansion that you don't see if you just stick with this. But if you probe the large order behavior beyond this, you suddenly see a huge network of relations with the other saddles. And remember, these other saddles are different exponentials, so these are non-perturbative contributions if your original starting point is a perturbative contribution. So this is generically true. I mean, there's some fine print that the function f can't be too crazy and whatever. Let's not worry about that. That's not important. This is one of the underlying reasons why we seem to see this type of behavior in problems in quantum mechanics and in field theory. And it gives you some hope, because the only way to prove this is via contour deformation. The fact that we already observe this behavior in quantum mechanical problems and in field theory, which are based on infinite dimensional exponential integrals, that gives you some hope that you can actually make sense of contour deformation in the infinite dimensional context. Because if you couldn't, this wouldn't be true. Okay, so it's not really a strong proof, but it's motivation that things could have died at this point and they didn't.
Sorry, actually I'm a bit confused. So how did you get the second equation in this slide from the first one?
Here, you just expand in g squared.
Expand in g square.
Yeah, and then you look at large orders in this expansion.
Okay.
And they're related to a saddle expansion of this. Right? The point is that it's the large orders here are related to the low orders here. Right? This is r goes to infinity. This is r equals 0, 1, 2.
So, so the fluctuation at one singular point is related to the fluctuation at all other singular points.
All, we need to be careful about the word all. So it's not necessarily all. That now depends on the function. This is the really complicated part of the story when you go to infinite dimensions. I'll talk more about that tomorrow. Here, let me just show you an example. So let's do the zero-dimensional partition function with sine squared. So this is just a Bessel function. We know everything about that function, so we can check everything, make sure we're not making mistakes. This clearly has two saddle points at 0 and pi over 2. This one's a minimum, this one's a saddle. You can do the expansions, it's complete triviality to do those expansions around those 2 points. Here are the expansion coefficients around 0. They're just factorials. So there are 2 factorials on top, 1 on bottom, so this is growing factorially. It goes like r minus 1 factorial. You look at the subleading expansions, and there are some weird numbers here. Right? So just tell Mathematica to expand this ratio. And now, so this is the large order behavior around this point. And now you go and look at the other point, the other saddle. In this case, there are only two. You look at the other one, and you just calculate the expansions, not large order, just look at the first few terms. Right? They're just the same numbers. So it looks like magic. Just take your favorite special function, just take Abramovitz, drop it on the ground, wherever it opens, look at that function, do this integral. It's just guaranteed to work. Okay? The surprise is that we've seen this type of behavior in infinite dimensional contexts. Exactly the same behavior. Okay? There's no reason that this machinery should uplift to infinite dimensions. So here's exercise 3. Do this for the Bessel function, modified Bessel function, but now with an extra twist that there's a parameter of the Bessel function. So here's the exercise. I gave you the coefficients. Just ask Mathematic to expand them and check that you really get the low orders of the expansion around the other point. Okay? So that's exercise 3. Very instructive. You can do it for any special function you choose. And we'll do this for nonlinear equations tomorrow. This is actually related to something that you could have learned in high school. I don't know if you would, maybe not. Think of a convergent function, a convergent expansion. If you have a function that has a branch point at some particular point z0, so it has a branch point with order g and then multiplied by some analytic function, then if you look at the expansion of this function around 0, not around z0, but around 0, we all know that the radius of convergence is fixed by the nearest singularity, right? So that's z0, is the radius of convergence. But if you look at the growth of those coefficients around 0, they grow with this combinatorial factor. So that first of all, they have the location. The power is the location of the branch point. That's not a surprise. But the leading rate of growth is this combinatorial factor. If you know that, you know what G is. You now know what type of branch cut it is, just by looking at the expansion around 0. And you also learn the leading term of the function multiplying the branch point. And if you do a little bit more work and work out the next subleading term at large order, you learn the first derivative of this function. And then you learn the second derivative. So you can reconstruct everything about the behavior in the vicinity of a singularity, even for a convergent expansion. Okay? If it's a log branch cut, same story. It's just similar. Exercise 4, check this for the hypergeometric function. That has a nice, interesting branch cut. These show up everywhere in the conformal bootstrap. So these have a branch cut at 1 going off to infinity. The behavior near that branch cut is completely characterized by the expansion around 0. So we want to talk about the Airy function. So I have sort of 5 minutes maybe, right? 10 minutes? Okay. All right. So I'm not going to finish what I wanted to finish today, but I want to solve the Airy function in 2 different ways. I want to solve it using perturbation theory, and then I want to solve it using a path integral. And the reason I want to do this is, remember, this was this sort of cartoon problem of a Minkowski functional integral versus a Euclidean functional integral. So I really want to work this to death because it has a huge amount of physics in it, and it's very simple. So imagine we have the differential equation for the Airy function, and you're interested in how the solution behaves at large x. So it's pretty clear from this that at large x, the behavior is exponential, because I need something that with 2 derivatives gives me a factor of x, which means when I take a derivative, I need to get a factor of root x, which means it has to be e to the x to the 3 halves with a factor of 2/3. Okay? If you look at the next order, you learn what the prefactor is, that it's x to the 1/4. And then if you do a little bit more work, you make an expansion, you can generate all the coefficients of the large x expansion. So this is the analog of being presented with a problem and somebody asked you to make a perturbative expansion. Somebody gave you this differential equation and said, expand at large x. This is exactly what you would do. Okay? Now, up to this exponential, this is a divergent series because there are 2 factorials on top and 1 on bottom, so there's a net factorial growth. Right? So we're back in the land of dealing with formal perturbative series, asymptotic series. Now here's the problem. If you just had this, which is a true formula at x equals plus infinity, and you looked at this formula and you changed the sign of x to the 3/2, which you can do by rotating x by 2 pi over 3. Well, you change the sign of this, so you interchange the plus and minus, and you interchange this plus and minus. So it looks as though you just turned area AI into area BI, right? The 2 independent solutions. Okay? So if you just looked at this, you would think that the area AI evaluated at e to the 2 pi over 3 times x is just area BI, up to some factor. Right? So it turns out that's not correct. The correct connection formula is that the area function rotated by that amount is indeed related to BI, but there's a non-perturbative piece which is exponentially small compared to this. Remember, this thing grows exponentially, whereas this thing decays. Okay? So this is exponentially small compared to this, so this is one of these guys that's usually ignored. Okay? It's exponentially small compared to any of these terms, so let's not worry about it. So I'm going to show you how to rediscover that term using Borel summation. So here, anyway, I don't want to bother too much about this. You can look at them on the slides. There are some pictures to convince you that this really works. So, first step, what's the Borel transform? The Borel transform is you take the expansion coefficients, and for simplicity, I'm just going to deal with the series first, and then I'll put these back at the end. Okay? Formulas are too big to fit otherwise. So the Borel transform is the same coefficients, but I divide by n factorial. Okay? Now you look at that function, you say, I know that function. That's a hypergeometric function. So in this case, the Borel transform function is a function we know. It's some f21 function, but of minus t. I'm doing this for ai. So this has a branch cut from along the negative axis from -1 to -infinity. Okay? Well, that's okay because I'm integrating from 0 to infinity, so I don't care. The point is, if I use this expansion, do those integrals, I get back to the original series. So that's good. Now the question is, what happens when I rotate x? Or rotate x to the 3/2. Let's think of it that way. So I can, as I rotate the phase of x to the 3/2, I can simultaneously rotate the t contour in such a way that it doesn't change, that this exponential doesn't change, right? Is that clear? The only possible problem is if I tried to cross that cut. Okay, this is in the t plane. So I can get to minus from above or from below, but I can't cross the cut. Okay. Now, the difference between going above and below is the jump across the cut. And now we see resurgence. The jump of this function across the cut is the same function at 1 minus t. It's not some other random function. It's the same function. Okay? Amazing. You plug that in to here with the rotated contour, and you discover that the difference of this integral rotating this way compared to rotating that way is just something involving this function, which is the same thing you started with multiplied by an extra phase factor, not phase factor, exponential factor. And that's the exponentially small thing that gives you this term. Okay? So if you just look at the series itself, you make a mistake. If you make a Borel transform and look at the Borel integral and are just careful about cuts and whatever, you can't possibly make a mistake. Okay? So the non-perturbative information is encoded in this Borel transform. So exercise 5 is just fill in the dots. I told you the strategy. It's not that complicated, and it's very instructive exercise. Okay, so okay, let me just give you a hint. So imagine we try to solve this problem now from a path integral, which means instead of taking the area function constructed from the differential equation perturbatively, I'm going to say my area function is defined by this integral. Okay? But that integral is oscillatory and hopeless, so I have to turn it into something that I can actually evaluate. I think I'll wait and do this tomorrow. The strategy will just be to do this, show that we can understand where this non-perturbative jump comes from in the sort of path integral language and how it corresponds to the Borel case. And then what we'll do tomorrow is we'll then look at a nonlinear equation, which is one that underlies a lot of these matrix models and simple versions of string theories, which is essentially the nonlinear version of this problem. And we'll see that when we do the nonlinear version, the same resurgent structure is there with a few interesting new features. Okay, that's enough for today. Thanks.
I mean, when you're relating this coefficient of different setters,
Yeah.
when you have this contour, I mean, is a statement following particular contour, steepest descent, or is it sort of room too bigger?
So you can deform, so asymptotically they have to follow the steepest descent contours. You can deform them within that, within reason, unless if you cross something else, you have to take into account that crossing.
I see, does coefficient remain
Yeah.
the same?
But let me say that this is one-dimensional.
Right.
Even in two complex dimensions, this becomes an extremely non-trivial problem in cohomology. So the mathematical approach to this problem, when you go even to multi-dimensions, let alone infinite dimensions, is you translate this problem into a cohomology problem and try to use methods, algebraic methods, to try and solve this. Because, I don't know about you, but thinking about even two-dimensional complex space and deforming contours is non-trivial, let alone infinite dimensions.
Sounds good.
Is the all the function which has all the series which has this resurgence property is a solution of some differential equation, or is it not necessary?
No. So there's a concept in mathematics called natural problems. I pressed mathematicians on what this actually means. So let me give you my version of the answer. If you have any system of equations, they could be integral equations, they could be differential equations, they could be difference equations, they could be anything, but there's some formalism for generating a solution. Under those circumstances, it's absolutely guaranteed. Okay? What it means is you could invent a series, right? You could just pick coefficients of a series, and you could construct some weird series and say that, at the 15,000th term, I'm going to change the coefficients to something else. Okay, that doesn't come from a natural physics problem. Right?
I guess that probably what you say is roughly the same as what I got. The impression that is, as far as some function is determined by some finite piece of information.
It doesn't have to be finite. I'll show you examples where they're infinite. So you can
then, from infinite information, I guess there is no necessity to, repeat the same information appear again and again, right? So what I mean is that resurgence is a repetition of the property, right? And probably that is just because that function is invented by simple, maybe recursion relation or differential equation or some finite set of information.
Maybe. It's certainly true that if you have some differential structure or different structure, it's easier to understand this. But I think that's a little too strong.
Anyone else?
Is there any physical example where you have to do the Borel transform twice or more to make it converge?
I don't understand what you mean.
So when the coefficient goes like n factorial, you have to Borel transform to make it convergent?
Well, n factor, what do you mean? N factorial to the power 100 or something? But
Yes,
it's
maybe.
100n factorial, so you would divide is 100n factorial. It's a leading order. So
Maybe. N factorial to n
no,
factorial.
it's actually a very interesting question. There are, in the approximation theory literature, there are things that change when you go above 2n factorial. Okay? It's actually quite interesting. But if something were diverging like 3n factorial, the Borel procedure would just be divide by 3n factorial. So you only need to do it once. But there are these subtle changes that happen there. And what's interesting about that is in almost all physics problems, it's either n factorial or 2n factorial. Is that a coincidence? Is that a fact that that's a general property of the types of differential equations we deal with? I'm not sure. But that's how you deal with a faster factorial.
Anyone else? No, otherwise let's thank Gerard again.